Hi, good morning, everyone. I'm Awais Khan from Sogang University, Seoul, South Korea. Today, I will talk about our work and analysis of system balance and architectural trends based on top 500 supercomputers. This work has been done in collaboration with Oak Ridge National Laboratory, Virginia Tech, Micron Tech, and closely supervised by Professor Youngji Kim. This is the agenda for my today's presentation. I will briefly discuss about supercomputers and then following top 500 listings. A supercomputer is a computer system equipped with great speed, high memory, high computation power, and of course, large storage capacity. The representative examples of supercomputers are Summit, Cori, Titan. For several decades, the supercomputers have provided the needed resources for modeling, simulation, and data analysis in numerous scientific domains. They're being used for solving weather forecast, different analysis and data information, AI, MLDL applications, astronomical observation, and solving large scientific calculations and problems. Top 500 list provides an excellent service to the HPC community by meticulously compiling the leading supercomputers from the world based on high performance lean pack benchmark and publishing this list biannually since 1993. Between the period 1993 and 2009, the project website Top 500 has published 54 lists encompassing more than 10,709 supercomputers from 2,894 institutions globally. This list basically reports the key architectural highlights, processor, interconnects, memory, power, storage, and flop scores, basically theoretical and the maximum achievable score of the supercomputer. I will briefly discuss about the supercomputer. I will give the motivation of my talk now. The supercomputer design is a complex multi-dimensional optimization process in which several aforementioned vectors need to be reconciled to meet a desired figure of merit of performance for a portfolio of applications and budget constraint. For example, the goal of Submit Computer hosted at Oak Ridge National Laboratory with 200 petaflop theoretical peak and was ranked as the number one in June 2019 top 500 list was to achieve the 5 to 10 times performance improvement over its predecessor Titan, which had 27 petaflop of theoretical performance. Further, the application workloads and application transformations and traditional simulation and analysis have been transforming over the time, and several supercomputing centers have to deal with new and emerging machine and deep learning codes on top of the traditional modeling and simulation applications. Thus, during this process, it is very natural that certain subsystems will be prioritized over certain others. Therefore, what is needed is a careful consideration of the overall system balance and how the various subsystems reconcile with one another. Designers need to be to understand the trends not only inside the individual subsystems of the supercomputer, but also with respect to one another. For example, one needs to understand the flops trends in accelerators-based heterogeneous processor versus many-core processor architectures, but at the same time glean the nuances in flops to memory bandwidth, our memory capacity ratios, our memory bandwidth to intra-node connectivity bandwidth ratios, our file system to memory subsystem ratios, our interconnect to flops ratios. Therefore, it is really important to understand the trade-offs between various subsystems to enable system designers to reconcile and provision the subsystems very carefully instead of producing suboptimal configurations of subsystems in supercomputer that may be prone to multiple performance bottlenecks. Next, I will describe our key contributions in this work. So in this work, we conducted a detailed analysis of 27 years of top 500 lists since 1993 till 2019, studying 10,709 supercomputers across several dimensions. Basically, we used three-dimensional analysis as The analysis one comprises of overall performance trends in top 500 supercomputers. Top 500 adopts the HPL benchmark score for normalizing the performance and ranking the supercomputers in the list. However, we believe that HPL score is a macro benchmark for measuring the aggregated processing power, and the score alone is a limited metric when it comes to unveiling the sophisticated and architectural trends in supercomputers. Thus, we analyze the individual performance factors and find their correlation with the HPL scores. The second analysis comprises of 28 recent supercomputers ranked as number one in top 500 list. In this dimension, we go a little deeper into the supercomputer architecture trend and analyze the performance balance of the recent top five supercomputers on the top 500 list in the past decade, starting from 2009 till 2019. Specifically, we collect the detailed information and show the performance balance between processing power and other subsystems in a supercomputer: memory, storage, bus buffer, and network, etc. Our third analysis consists of the purely 16 heterogeneous supercomputers, which, as the trend of heterogeneous supercomputers is becoming increasingly popular for achieving the desired system efficiency within the given budget and energy requirements. Thus, we aim to identify the key architectural trends and balance ratios from recent heterogeneous systems. For example, intranode connectivity, memory subsystem balance, and acquire insights for designing future systems. An important thing to mention here, to note here, is that our complete dataset is publicly available on the GitHub. The link can be found in the slide footer of this slide. Now I will move to our first analysis, which is overall performance trend in top 500 supercomputers. We analyze the trend in HPL scores of all 10,709 supercomputers that have appeared in top 500 between 1993 up till 2019. We can see the trend of RMAX scores, the maximum observed performance of all supercomputers that have appeared in top 500 listings in 1993. The trend shows that on average, a newly introduced number one supercomputer has doubled the RMAX scores of its immediate predecessor. For example, ASCII Red in 1997 was recorded as the first supercomputer with a teraflop per second performance, while the Roadrunner 2008 was the first petascale supercomputer. We also compare the performance of these number one machines against the prediction of Moore's law. Specifically, we normalize the RMAX scores of number one machines based on the RMAX score of the CM51024, the number one machine in June 1993. So we observed that all the number one machines since 1997 performed beyond the prediction of the Moore's law. For example, the RMAX score of Tiane 2A in 2013 exceeds the projection of Moore's law by almost 100 times, whereas the most recent supercomputer summit exhibits RMAX that surpasses the projection by 18 times. Another important metric in evaluating system performance in energy is energy efficiency, which is often measured by flops per watt. We clearly observe an increasing trend in energy efficiency in supercomputers starting from 2005. One thing that to mention here is that we did our analysis starting from 2005, as earlier top 500 listings do not provide the power consumption data. And we can clearly say that for each listing, the median energy efficiency of the corresponding top 500 systems has increased 1.2x on average. In addition, with exceptions of 2005, the energy efficiency of number one supercomputer is steadily positioned within the top 25%, demonstrating that the number one machines tend to run more energy efficiently than the other machines. To further investigate and validate our observation, we analyze the correlation between top 500 rank and energy efficiency. So each point in the bottom plot specifies the Pearson's correlation coefficient, where the energy efficiency is described as a function of the rank in the corresponding top 500 listing. We observed that a strong negative correlation exists in earlier years. that is, high performance supercomputers become being less energy efficient, which is no longer the case in recent years, although no positive correlation exists. Evidently, Summit Supercomputer 2018 and 2019, the number one supercomputer in top 500, is also ranked as number two in the Green 500 list for June 2019. Next, I will show the trend in annual performance efficiency of supercomputers, and the performance efficiency is defined as a ratio of theoretical R max to R peak, which is basically the performance achieved after running the benchmark HPL benchmark, divided by the total theoretical performance of the supercomputer. The average performance efficiency of 10,709 subsystems RPEAK is 0.67, indicating that most machines merely achieve less than 70% of their theoretical performance. Unlike previous power efficiency trends, we do not observe an increasing trend in performance efficiency. We observe that the performance efficiency of K computer in year 2011 is 0.93, while 77% of number one supercomputers, 40 basic exact to be precise, 40 out of 52 record performance efficiency scores below the overall median, which is 0.67. A key factor in achieving HPL score is to have a very strong correlation between the performance and the system attributes. Therefore, in order to have a high HPL score, one needs to have a strong computing power. So for this purpose, recent supercomputers tend to be equipped with massive number of computing cores. So we analyze that how the total core count of a supercomputer affects its RMAX score. Specifically, we performed a correlation analysis between RMAX score and the total core count for each year. Our analysis shows that the coefficient between RMAX and total core count is highest between 2013 and 2016. That is 0.95 on average. Surprisingly, the correlation drops drastically starting from 2017. That the average correlation between 2017 and 2000 is only 0.66, more than 30% lower than the previous year. One reason for this lower correlation, weaker correlation, is attributed to the increasing number of heterogeneous supercomputers. So further details can be found in the paper. The rectangle boxes in the figure shows the correlation between HPL scores and memory capacity. Starting from late 2009, we can observe that the correlation between HPL score and memory capacity becomes noticeably higher. The bottom plot shows the percentage of heterogeneous supercomputers, that is systems with additional accelerator processors such as GPU, in the recent top 500 listings. For the past 8 years, the number of heterogeneous systems in the listing has steadily increased. That is 1% of 1% are the 5 systems annually. They occupy about 28% of the almost out of the 500 or out of the 100%. In November 2019. We expect that this increasing trend will continue, particularly for addressing technological limitations and also for controlling the power consumption. Next, I will discuss our second analysis, which is balance trends in recent supercomputers. In this analysis, we go deeper on the performance trend in recent top 5 supercomputers from all the lists starting from 2009 till 2019. Specifically, we focus on supercomputers that have been ranked in top 5 positions on top 500 listings in the last decade, between 2009 and 2019. As shown in the table, our target supercomputers consist of 16 heterogeneous and 12 traditional supercomputers. And it starts with Blue Gene L and ends with the Frontera. In order to study the heterogeneous supercomputers and the traditional supercomputers, first we analyze the overall system efficiency in 2 variants. The first one is power efficiency, performance efficiency, which can be derived as R max ratio R peak, and power efficiency as a function of R max to the ratio of power of 28 supercomputers appearing in top 5. The trend shows that the heterogeneous systems tend to dominate the architectural trend in the top supercomputers. Particularly since November 2017, all top five supercomputers are heterogeneous, indicating the increasing popularity of the heterogeneous architecture. Further, we can notice that the heterogeneous systems tend to exhibit a lower performance efficiency, that is, achieving less than 80% of the theoretical peak performance, which is our peak. Similarly, the power efficiency of the heterogeneous systems far exceed that of traditional systems, especially since 2017. Specifically, the average of power efficiency of the heterogeneous machines, 5.5 gigaflops per watt, is about 5 times higher than the average power efficiency of the traditional machines, which is 1.1 gigaflops per watt. Our observations clearly demonstrates that the benefit, that is energy efficiency, and also challenges, that is technical obstacles to realize the potential performance of the heterogeneous architectures. Next, we show the balance trend in memory subsystem. For heterogeneous systems, the memory capacity and the bandwidth are the sums of the DRAM and HBM capacity and the bandwidth in our analysis. The top figure shows the trend in the memory capacity per core, that is summation of memory capacity to the ratio of summation of cores, total cores of the recent top five machines from every year. We observed that the most systems are clustered around 1 GB in the graph. Only three supercomputers, Jaguar 1, K computer, and Super MUC, furnish more than 2 GB of memory per processing core. In addition to the per core memory capacity of the heterogeneous supercomputers, zero point 0.7 GB on average tend to be lower than the per core memory of the traditional systems, which is almost 1.3 GB on average. Although the heterogeneous systems tend to be equipped with a greater amount of system memory capacity, more than 300 terabytes on average, the bottom figure depicts the performance balance between the aggregate memory bandwidth and the peak processing power, which can be derived as a summation of memory bandwidth to the ratio of theoretical performance R peak of the target supercomputers. Overall, we clearly see a diminishing trend in the balance ratio, indicating that the processing power grows faster than the system memory speed. For instance, the highest ratio value in 2019, that is 0.13 from Summit, is about 9 times lower than the highest ratio in 2009, that is 1.2 from the Blue Gene L. Further, after 2011, none of the top systems exceed zero point 0.5 by zero point 0.5 GB per flops, bytes per second per flops. Most supercomputers are equipped with a network parallel file system to support capacity requirements of the running application. The memory is inevitably used as a buffer space for manipulating datasets in the parallel file systems deployed in these supercomputers. Therefore, we analyze the performance balance between the PFS and the memory subsystems. For the file system capacity, we observe that the ratio values are scattered between 2 and 100, except for the two systems, that is Pleiades and Gaioku, which provide substantially larger file system space compared to their memory capacity, that is 140x and 410x respectively. These details can be found in the paper and in the table in the earlier slides. The overall average ratio is 44, meaning that the recent top supercomputers tend to provision the parallel file system capacity to be 44 times larger than their memory capacity. In addition, Summit, the number one supercomputer in 2018 and 2019, has a ratio of 89, almost 2 times greater than the overall average performance. Similar to the capacity ratio, we do not observe a clear change the time in the bandwidth ratio over the time in the bandwidth ratio. On average, the file system bandwidth in the recent top systems are 13,353 times lower than the aggregate memory bandwidth. Although we had observed a significant variance among these systems, the parallel file system in Summit is about 10,000 times lower than its aggregate memory speed, justifying a bus buffer, a need of a bus buffer. Next, I will talk about our third analysis, focusing architectural balance in heterogeneous supercomputers. We analyzed the architectural trend and the performance balance in intra-node connectivity of the 16 heterogeneous supercomputers from the 28 top recent supercomputers discussed in our analysis too. With emerging heterogeneous architectures and data-intensive application demands, achieving the performance balance between the system components has become more important than it was in the past. We first analyze the proportion of the accelerators in the overall systems for the 16 heterogeneous supercomputers. The top figure depicts the flops, which is a theoretical peak performance or peak ratio between the conventional CPU and the accelerators for each heterogeneous systems. It is clearly noticeable that the accelerator dominates the overall performance in most heterogeneous systems. For 16 heterogeneous systems, the accelerator contribute up to 84% of the R peak on average. And Jaguar 2 is the only machine wherein the accelerator produced less than 50% of the system's R peak. Recent Summit, Sierra, Frontera systems rely on the accelerator for more than 95% of the overall system's flops. This indicates that it is essential to utilize the accelerators efficiently to fully exploit the processing power of the heterogeneous supercomputers. The lower figure shows the capacity between the DRAM for CPUs and HBM for accelerators. Despite the strong dominance of the acceleration in RPEAK, the DRAM capacity still dominates the HBM capacity in many heterogeneous systems. HBM is high bandwidth memory. On average, we can observe that on average, DRAM provides 68% of the total system memory capacity. There are several other analyses and observations in form of the results in the paper, but due to time limit, I will skip. For more details, please refer to our paper. Now I will conclude my talk. We collected and analyzed data of over 10,000 supercomputers from the top 500 list, which is published by annually across the globe based on the HPL scores. We presented and analyzed a versatile and multidimensional analysis over the collected top 500 supercomputer datasets. We claim that our analysis provides a set of useful insights and guidelines to the system designers for understanding the architectural trends architectural trends and to design next generation supercomputers with a balance between the supercomputer subsystems. Thank you so much for listening to my talk. Please feel free to drop your questions via email on awaz@sogang.ac.kr. Thank you so much.